Here at the midpoint of our Calculus 2 class, we're going to leave the study of integration for a while and we're going to take up the study of sequences and series. Now, in the English language, the word sequence and series seem to be interchangeable, but in mathematics, they are different structures. To understand what a series is, we're going to build a foundation of what a sequence is. So let's begin there. Definition. A sequence is going to represent a set, and anytime we denote a set in mathematics, we do so with curly braces. So we're looking at a set of elements that are described by this general term a sub n. A sub n is the term of the sequence, where n is the index of that particular term. So this sequence is a list of numbers of the form a sub 1, a sub 2, continuing this pattern, ... till we get to some general term, a sub n, and ... means that pattern continues. So the subscript of each term indicates the position of that term in the sequence. So a sub 1 is the first term, a sub 2 is the second term. A sub n just represents a general member of that sequence somewhere down the line. Now, sequences may be finite or infinite. In the case of this type of notation, we have a sequence, a sub n, where the first value of the index is 1 and the final value of the index is 10. So that particular sequence has 10 elements. In the case of an infinite sequence, we start counting at the subscript 1 and continue indefinitely, represented here by an infinite upper limit. So a sequence is simply a list of numbers, and generally this list has a specific pattern. Let's see if we can use the principle of induction to crack these codes. In example 1a, we have a pattern or a sequence of numbers, 1, 4, 9, 16. So in order to figure out the next two terms of the sequence, I'm going to attempt to detect a pattern or a commonality in the first few terms. Now, because of your experience in math classes, you probably instantly recognize these to be perfect squares. So the first term is 1 squared, the second term is 2 squared, followed by 3 squared, 4 squared, and so 5 squared or 25 would be the next term. And then of course 6 squared or 36. So in this case, we are looking at the pattern of perfect squares. Consider example B. We have the values 1, 1, 2, 3, 5, and our job is to figure out the next two terms in the sequence. Now, this is actually a famous sequence. It's called the Fibonacci sequence. So the values that we're looking at here are called Fibonacci numbers. Now, do you know how to determine the next element in the sequence? Well, if you look closely, we can determine this value recursively. So, for example, look at 2. Notice that 2 is the sum of the two previous terms. This happens again with 3. Notice that this element is the sum of the two previous terms, and this pattern continues. So if I want to find this next unknown number, I'm going to add the two previous terms to get 8. And then finally, I can add these two numbers to get 13. So again, this is a famous sequence called the Fibonacci sequence, and if you have some time, it's really interesting. Do a little bit of research about it. The Fibonacci sequence is connected to organic growth, all kinds of interesting things that appear in nature. Let's look at the next example, 1, 2, 6, and 24. To figure out this pattern, again, I'm going to think about it recursively. That is, how did I obtain this term by doing some sort of operation to the previous term? So notice I can multiply that first term by 2 to get the second one. From here to here, we multiplied by 3. From here to here, we multiplied by 4. So the next, if we continue this pattern, the next logical step would be to multiply by 5 to get 120. And then again, multiply by 6 to get 720. Now, to work these problems, we're really just depending on our ability to recognize a pattern, and a lot of that ability is based on your experience with previous math classes. we thought about each of these problems a little bit differently. Problem A, pattern A, we were thinking about in terms of its position. So we were squaring a position to generate the outcome. But the second two, we were thinking about in terms of recursive terms, or how do I generate the next term in terms of the previous terms that came before it. But if we use the same framework to understand the sequence in example C, you also might recognize these as a pattern of factorials. Now, we generated each term based on the previous term, but you might also recognize these to be factorial values. If you've had any experience with statistics or probability, you might recognize those. So our approach here again is twofold. We're looking at something called an explicit formula and something called a recursive formula. So let's go ahead and look at those two different approaches. The first way to think about the terms of the sequence is by an explicit formula. An explicit formula defines the nth term of the sequence in terms of its position in. This is also known as the general term. This is how we thought about example 1a above. I was looking at the position of each of those elements in the sequence, squaring the position to obtain the term of the sequence. So for example 1a, we could say the explicit formula for the terms of the sequence is given by n squared. Take the position and square it and generate the output. So an explicit formula is given as a function of n, where n is the position of the term in the sequence. For example, write the first four terms of the sequence given by a sub n equals negative 2/3 to the nth power. This is an explicit formula, also known as an nth term formula or the general term. So to find a sub 1, the first term in the sequence, I'm simply going to plug 1 in for n and evaluate. So the first term of our sequence here is negative 2/3. The second term, we're going to plug 2 in for n. So we have negative 2/3 squared or 4/9. To get the third term of the sequence, we're going to plug the position 3 in for n. We would end up with negative 8/27. And finally, the fourth term, we're plugging 4 in for n, and we obtain 16/81. So the first four terms of this sequence would be negative 2/3, positive 4/9, negative 8/27, and 16/81. Notice we have what's called an alternating sequence, or a sequence in which the sign changes from term to term. The benefit of an explicit or an nth term formula is that I could also ask you, well, what's the 100th term of this sequence? All I would have to do is plug in n equals 100. I could jump way down to the 100th term in the sequence without having to know the first 99 and use that nth term formula to generate that particular value. So the nth term formula is desirable and very useful, and it will be to our study of series as well. Another approach to defining a sequence is by using a recursive formula. A recursive formula, also known as an implicit formula or recurrence relation, gives a formula for each term of the sequence based on previous terms. This is how we thought about examples B and C in example 1. Recall that we generated this term of the sequence by applying an operation to the previous term. We determined this one by applying an operation to the previous terms. Same thing here. We were looking at what sort of operation can I do to the previous term to generate the next term. That's called thinking about that pattern recursively. A recursive formula, also known as a recurrence relation or implicit formula, is going to define the terms of the sequence based on previous terms. For example, write the first 4 terms of the sequence given by a sub 1 equals 4 and a sub n plus 1 equals n plus 1 over 2 a sub n. So to get the nth term of the sequence, or I'm sorry, let me say it this way. To get the n plus first term of the sequence, I'm going to need to know the term that came before it. And anytime we have a recurrence relation, we always have to have a place to begin. So the first term of our sequence is defined as a sub 1 equals 4. Now, to find a sub 2, we're going to plug in n equals 1. Now, that might be a little bit confusing, but notice to get a sub 2, it's going to be in terms of a sub 1. So if I use this formula, what plus 1 equals 2? We're using n equals 1. So plugging in 1 for n, we end up with 2 over 2 times a sub 1, or just a sub 1, which is also 4. Okay, let's try that again. To get a sub 3, okay, notice if I'm trying to find a sub 3, it's going to be in terms of a sub 2. So in this case, we're plugging in n equals 2. So we'll end up with 2 plus 1 over 2 times a sub 2, or 3 halves times a sub 2. Remember, previously we found a sub 2 to be equal to 4. So when we reduce here, our next term is 6. To get the fourth term of the sequence, we're going to need to know a sub 3. If n plus 1 is 4, then it looks like n is 3. So we end up with 3 plus 1 over 2 times the previous term, a sub 3. Or 4 over 2, which reduces to 2, times a sub 3, which is 6, or 12. So the first 4 terms of the sequence are 4, 4, 6, and 12. So the 2 different ways to define a sequence are using an explicit or nth term formula. In that case, the value of the sequence is given in terms of its position in. Or in terms of a recursive or recurrence relation, then the term in the sequence is defined based on the term or terms that came before it. And in that case, you always have to have a starting point. So let's try example 4, where we find both a recursive and explicit formula for the given sequence. Generally, your brain is going to pick up on the recursive formula before the explicit formula. So let's begin there. In example A, we have the pattern 1, 1/2, 1/4, 1/8, 1/16. You probably notice very quickly that each time the denominator is doubling. So we could say the first term is 1, and then the next term is 1/2 times the one that came before. This is what we call a recursive formula. Now, what's generally more challenging is defining the explicit formula. In this case, I don't want to think about the terms based on the nature of the previous terms. I want to figure out, how can I write each term as a function of its position? So if this is the first position, this would be the second position, third, fourth, and fifth. So I want to know what's the connection between the term of the sequence and its position. Notice in the denominator we do have powers of 2. So I'm going to think of this first denominator as 2 to the first power. This would be 2 to the second power, 2 to the third power, and 2 to the fourth power. If I want to be consistent, I can say that one's 1 over 2 to the 0th power. Now look at the connection between the power or the exponent on the 2 and the position. Notice in each case the power is 1 less than the position. So we could say a sub n is equal to 1 over 2 times position n minus 1. This is the explicit or nth term formula. So once again, the recursive formula defines each term of the sequence in terms of the one that came before, whereas the nth term, or explicit formula, defines the value of the sequence in terms of its position in. Let's try this with the next example. We have the pattern 1, -2, 3, -4, 5. This is what we call an alternating sequence, where each successive term changes sign. Now, without the alternation in sign here, the pattern would be very simple: 1, 2, 3, 4, 5. So let's begin with our recursive formula. Remember, with a recursive formula, you always define your first term. Then the next term will be given in terms of the one that came before. So if for a moment I ignore the alternation in sign, I know that from here to here I've added 1, and from here to here I've added 1. And if I think about the alternation in sign, while I'm adding 1, I'm multiplying the result by -1. So we could say this is -1 times the previous term plus 1. And let me be very careful here. Let's get absolute value bars around that a sub n. So again, to generate each term, I take the absolute value of the previous term and I add 1 to it, and then I'm going to multiply it by -1, and that causes the sign to alternate. So that is our recursive formula for this one. Moving on to the explicit or nth term formula, now I want to figure out the definition of each term in terms of its position. So this is the first term, this is the second term, this is the third term, this is the fourth term, and this is the fifth term. So what I'm doing here is recognizing the position of each term in the sequence, which we know will be the n in our formula. So obviously, in each case, the position at least generates the absolute value of the term. To get the sign to alternate, we can simply multiply it by a power of -1. In this case, we could write it as -1 to the n plus 1 times n. Notice, if n is equal to 1, we have -1 squared, which gives me a positive 1. If n is equal to 2, we have -1 raised to the third power, which gives me an odd number of negatives, or a negative sign, so -1 times 2. So this gives us our explicit formula. In both of these cases, your brain is very likely to notice the recursive formula first. How do I obtain subsequent terms based on the previous terms? But the most valuable one to us mathematically will be the explicit formula. Again, the benefit of the explicit formula is if I wanted to, I could use this term to find a sub 100, the 100th term of the sequence, without having to know the first 99 terms. So this is our introduction to sequences. You've got two ways of expressing a sequence, recursively or explicitly, and we'll get a little bit more practice with that explicit formula coming up soon.